Most methods included in the Express Python module accept arguments in the form of lists, dictionaries, and sets. This enables users to speed up their model building time by avoiding using explicit loops, which can make a significant difference for large optimization models with a high number of calls to methods such as add variable and add constraint. For example, calling the method add constraint for each element in an explicit loop is highly inefficient as compared to using an inner loop as part of the add constraint argument. Another hint for more compact and efficient modeling is to use data objects and express variables as NumPy arrays. By using the p.addVariables function with integer arguments, you can directly create multi-dimensional NumPy arrays with one or more zero-based indices. This enables the use of the xp.operator for carrying out dot operations in vectors and matrices, leveraging the broadcasting and vectorization features of NumPy for efficiency. In case the input data can be represented as sparse vectors or matrices, the use of the sparse module from the SciPy package can be leveraged. The xp.operator supports the most common SciPy sparse matrix formats, further decreasing the model building times for the cases where matrices have very low density. An alternative way of considerably reducing the model building effort is by using the low-level interface via the problem.loadProblem function, which takes all the model components as arguments. As an example of usage, consider the following model constructed with the high-level functions of the Python interface, with two decision variables, one being integer and having lower and upper bounds, two linear constraints added directly via expressions, and a quadratic objective function. Exactly the same problem can be built with a single call to problem.loadProblem with a series of arguments specifying the different model elements, such as constraint senses, coefficients for variables, constraints and objective, variable types, and scrambled variable names. Although this method requires some data preparation steps to convert data into a vectorial or matricial form, the gains in performance are significant when it comes to building the problem by avoiding multiple calls to high-level functions. The downside of this approach is a less easily human-readable model formulation that might require higher efforts for its maintenance. Examples of using the low-level API with the load problem capabilities can be found in the Python notebook example named load.lp. In this example, a simple linear programming problem is optimized by passing all the necessary arguments such as lists of constraint senses, right-hand side values, objective coefficients, and variable bounds and names, when calling the load problem function. Note that the start argument contains the offset for the start of the entries for each decision variable in the row indices and row coefficients arrays, as pictured in the table. The problem is then exported to a file with LP format before being optimized. The created LP file can be explored to validate the model formulation. Then, the objective function is replaced by a new quadratic objective function using the high-level API method problem.setObjective. The problem is optimized again, and the updated model file in LP format is again exported into the active working directory.